When you collect usable data of known quality, you need to provide evidence about the quality of your measurements, and you need to communicate what your data represents in the environment. The introduction in the first topic of this module reiterates the concept of measurement quality objectives and shows examples. It also talks about representativeness in terms of communicating the intent of the study, and discusses how the timing of your measurements can reflect your intent. Topic 2.2 discusses trip planning and preparation with a focus on water quality measurement, but you can easily integrate the same preparation for sample collection. For specific details related to water sampling, please refer to Module 4, Water Sampling. Topic 2.2 also provides the Field Kit checklist and refers you to other checklists to help you mount an expedition. Topic 2.3 of this module takes you through the process of instrument calibration and advises on what to record while calibrating or checking the accuracy of your instruments. Topic 2.4 is about field observations and how to communicate what you see. It also shows examples of common observation parameters and lists options for communication. Topic 2.5 reiterates where exactly in the water body to make the measurement, how to access that place with your probe, and what to do if you can't. Topic 2.6 is about measuring water quality parameters and capturing the information in a data sheet. Because the measurement procedures are varied and instrument-specific, only the common principles are shown. Please make sure you find and use the standard operating procedures that are specific to your instruments. And finally, Topic 2.7 lists some points to think about when selecting a location to deploy data loggers for continuous, unattended monitoring of basic water quality parameters, and describes the major steps in the process of using data loggers. Click on a topic to start, or click Next to see them in order. Welcome to the Water Quality Measurements module. As you can see by the activities highlighted in green on your screen, observations and water quality measurements are usually first in the series of field activities you perform during one station visit. If you plan to do all the activities shown, it makes sense to first identify a good area for sediment collection, where deposition occurs, and leave it undisturbed by moving downstream to do the other activities. You may do the observations anywhere, but start the activities that require wading well downstream of your fine sediment area. Then, move upstream for water and sediment collection. This module applies to all types of stations: streams and rivers, estuaries and wetlands, lakes and reservoirs, bays and harbors, and open water stations. It is assumed that you are already familiar with the purpose of the data to be collected, and that the stations have already been selected for that purpose. Measurement quality objectives, or MQOs, are statements about the extent of measurement error and uncertainty that we can tolerate and still be able to answer the study question. They are developed for several distinct aspects of data quality, such as accuracy and precision. This screen shows you the accuracy MQOs that have been previously recommended by SWAMP as an example. Accuracy is about how far we are from the true value. Good accuracy depends on timely calibrations of the instruments, so they do not drift far away from the calibrated state. Precision is how close one measurement is to another taken at the same place at the same time. And, naturally, good precision requires consistency in our operations. Other things we need to think about are related to the integrity of a measurement, which might be compromised if the instrument is dirty. Calibrating, being consistent, and keeping the instruments clean are actions you can implement to affect and improve the quality of your measurements. However, you will also need to check, record, and report the quality of your measurements so that you know you have met the MQOs. To do these checks, you will need to run post-monitoring accuracy checks, and to repeat your field measurements frequently so that you have enough pairs of repeated measurements to assess your precision. The next few sections will provide more information on these checks. Click the Read About Quality Assurance button to read about the big picture. When you are trying to find the best time to do your field measurements, you need to know what conditions you are required to document and go to the station accordingly. As you know, the values of temperature, dissolved oxygen, and pH change over the 24-hour period in relation to sunlight. The graph on your screen shows real data collected with a data logger in a small urban lake over 3 days. You can see from the diurnal variations in temperature, pH, and dissolved oxygen that the time of day of your measurement really does matter. So, if the intent of your study is to characterize the worst-case conditions for dissolved oxygen, you would come in at 5 or 6 a.m., because that is when the level is at its lowest. Please read the question about temperature and choose your answer. Then click the Answer button to see what the fish might tell you. When you deliberately choose the timing to target certain conditions based on your knowledge, you are using the targeted or directed sampling design principle. If you cannot be there in times that capture the conditions of interest, such as the worst-case scenario, try to use continuous monitoring devices with data loggers. For routine monitoring, try to visit each of your stations at the same time of day on every trip, so that all data points will represent the same diurnal conditions. In this case, you will be using this systematic, instead of directed, sampling design principle. If you want to apply the systematic monitoring design in the same way that others are often using it, then take all your measurements between 9 a.m. and 11 a.m. This time window is used by many watershed groups for their routine monitoring efforts, and you will be able to compare your results to what they are measuring in their stations. If you cannot control the timing of your station visits due to logistical constraints, you will be using a non-deliberate sampling design we often refer to as anecdotal. You might also deliberately show up at unexpected times, for example when you do your stream watch patrols. This fourth sampling design principle is called random. If you are not sure which design principle to use, consult your monitoring plan or your quality assurance project plan. Click on a topic to start, or click the Next button to see them in order. Before you do any scheduling, you want to know exactly where your stations are located and make sure you have legal access to all of them. If you were not the one conducting the reconnaissance, it would be very beneficial for you to read the site dossier. For more information about the site dossier, see the final topic in Module 1, Reconnaissance. If you need to assure access permission yourself, click the button to read more about this. Never trespass. Secure access permission, including keys and lock combinations if needed. When you plan a field trip, you can utilize a scheduling chart with placeholders for field crews to assure that there are enough members in each crew. Regional board swampers often send an email to the entire office to invite folks to participate in field trips. Many watershed organizations send a flyer to recruit volunteers from the community for a specific trip. The idea is that at least one member of the field crew has to be totally familiar with the field measurement procedures, but he or she can get help from others on certain tasks, even if they have not done it before. For example, a volunteer can be the appointed scribe and write information on the datasheet after a quick walkthrough. Or, someone can hold the pole and suspend your probe in the water exactly where it needs to be while you fiddle around with the display unit. The bottom line? You need all the hands you can get. Getting a crew or a buddy with you is also mandated by health and safety common sense. Never go out by yourself. By the time you check for vehicle availability, you should have learned about the roads you will need to use, so you can select a vehicle that will get you there and get you out of there too. You should also know how much equipment you will be carrying and how many people will ride with you. If you can use a fuel-efficient station wagon, by all means take that option. But if you need to use a gas-guzzling SUV or a truck, don't get lost because you will travel more miles than needed. Now that you are ready to start packing, it is a good idea to consult checklists that will help you remember what to bring. Click the Go to Mounting an Expedition button to see a generic list of things to do when mounting a field expedition. Make sure that you have what you need with you at all times in terms of licenses, agency affiliation identifiers, permission letters, or any other papers. Click on the Go to Checklists button to peruse the checklists that are relevant to your trip, whether they be personal, vehicle, or monitoring equipment. Take any checklist and amend it if this will help you keep track of equipment. For example, which instruments are in which box, which items are in which truck, and where the locks are located. It really helps if you pack your field gear in a way that will allow access to it in the order that you need it, and if you make sure that all the bits you need for one task are in one kit. If your field sampling instruments were bought with protective casing, use it. Make sure you know how to pack and stow gear to avoid damage by static electricity, water, dust, vibration, and so on. Choose boxes that are sturdy, easy to lock, and well padded, but do not get boxes that are too heavy for one person to handle when full, because we know someone will eventually try to lift it.
In addition to the sampling equipment, the bottles, the pull samplers, the various other containers, there's a lot of other equipment associated with field operations and the collection of water quality samples. And the organization and storage of these items is really critical to efficient field crew operation. So one of the purposes of this demonstration is just to show you what's available, what you can use. And generally, this particular container here at my feet, you can buy it at almost any hardware store. And it has a couple compartments for the storage of small items. Here we have Sharpies, things like that. Here's a little spider. These are really important. And then some string and a small box containing air. So these are very, very handy. And then over here we have a small triangle, and actually probably one of the most handiest tools is a multiple use screwdriver. Much more useful than the plastic spider. We also have a whole array of storage items. Plastic or paper bags. Now paper bags are not really very useful, and are more useful for storage of trash than anything else. The equipment should be put in containers that are at minimum crush proof and water resistant, if not waterproof. So we have buckets. This is a standard 5-gallon bucket, very handy for carrying bulky items, bottles, things like that. Has a handle on it. You can carry it around, very, very, very easy to carry. Ammunition boxes, extremely cheap, watertight, crush proof, excellent for small items. This is a standard carpenter's toolbox that we use to hold the equipment associated with our water quality multi-parameter instruments. And it has a top tray that will contain all the necessary. This is the membrane kit, screwdrivers, extra batteries, sound guard. These are extra O-rings and DO membranes and DO membrane O-rings. So all the things that you need. And then we have inside, of course, we have the sondes. And this, while not waterproof, is watertight, crush resistant, and protects this instrument very well. This is about a $5,000 instrument, so we don't really want to put it in a paper bag. Other field equipment. This is the standard large container with a lid. These are very, very good to sit on. They're very strong. You can stack them. And they contain all manner of associated equipment, gloves, wipes, handy wipes, things like that. Anything you want to put in here, this is all our medical equipment, things like that. Standard telephone box. This is very good for cameras. The camera that's in here isn't here. But again, the cameras always come with card readers now, extra mag cards, and USB cables, batteries, things like that. This keeps them in one place, keeps them secure, and you can put it behind your seat when you go sampling. Very inexpensive plastic box. Very good for handling. These are discrete, smaller water quality meters, instruction books, things like that. Anything, virtually anything. We then have, again, very standard container. This particular container is I use it for all my personal sampling equipment. I can just grab it and go anytime.
There is one step of special preparations you will need to do for field measurements if you intend to use a dissolved oxygen electrode. It is usually an extra step, beyond the routine maintenance that you will need to do with any measurement device, and you often have to do it as part of preparation for a trip. Read the manufacturer's instructions and consult with other swampers to determine the frequency of this operation. Click the button to play the video that shows how the electrode is assembled.
Proper care and maintenance of field equipment is essential for obtaining high-quality data. One of the things that is important in the maintenance facade is the dissolved oxygen membrane. And so this demonstration, I will show you how to replace the dissolved oxygen membrane on a YSI 600XL multi-probe. So first thing we do is we remove the probe cup, and you'll note this particular instrument has a dissolved oxygen membrane already installed. I'll remove it, but I want you to take a look and see the condition of those electrodes. They're very shiny, the membrane is smooth, and there's no wrinkles, there's no bubbles. The membrane is very closely cut to the side of the instrument, so there's no waste or no extra membrane hanging out on the side. So I'll remove the membrane now. Okay, now I will demonstrate how to install a dissolved oxygen membrane on a YSI 600XL dissolved oxygen probe. The probe from the manufacturer is clean and dry. You can see the probe here, the two shiny electrodes. And what we need to do is put an electrolyte in the probe. The probe has a slight recessed area, and that area will be filled with electrolyte, and then the dissolved oxygen membrane will be installed on top of that and secured with an O-ring. So the first thing we need to do is prepare the electrolyte, which comes dry, and we simply add deionized water, mix it, and we have the electrolyte. The electrolyte is then put on the dissolved oxygen membrane until it forms a positive meniscus. I think you can see that. There's a tiny bubble. We don't want any bubbles in there. So you can see that meniscus, that positive meniscus. Okay. I will then put a little more in there. Put the inside. The membrane. The membranes come in a little book, kind of like a matchbook. You open them up, and they have an adhesive pad right here, and that adhesive pad will catch one membrane, which you then take carefully in your hands and try not to touch the center part of the membrane. It's very thin but quite tough, and it's made out of Teflon. You then put the membrane on the side of the probe, hold it down firmly with your thumb, and then stretch the membrane across the top of the probe, securing it with your other finger. You then, without again touching the surface of the membrane, roll an O-ring on with your fingers, like that. You then see the membrane has a lot of extra on here. You make sure that the membrane is nice and taut, there's no bubbles, there's no wrinkles.
The excess membrane material is then trimmed with a pair of scissors or a sharp knife, taking particular care not to damage the probe or probe body.
You then want to wash off any extra electrolyte, and we're washing here with just tap water or deionized water. It doesn't really make any difference. And then the final inspection before we put the tap on. Okay, you can see the membrane is tight, no wrinkles, no bubbles, no excess membrane, and we're ready to put the protective cap on the instrument.
Now the instrument is not ready to use now, even though I installed the membrane. The membrane, being flexible Teflon, has to kind of relax after it's installed. You saw how I stretched it. So it takes between 6 and 8 hours to relax. So the instrument should not be used for at least 6 or 8 hours until that membrane is allowed to relax. And then it can be calibrated and used in the field.
Instrument calibration is an essential part of preparing for a field measurement trip. Each instrument will have its own procedure. Read the manufacturer's instructions and/or the instrument-specific standard operating procedures to find the step-by-step instructions for the calibration process. Consult the SWAMP Quality Assurance Project Plan for specific calibration frequency requirements. The next 3 screens in this topic explain the background concepts and provide information on the contents of data capture forms. Topic 2.3.1 explains what we mean when we talk about drift from the calibrated state. Topic 2.3.2 shows a list of the bits of information that need to be recorded when calibrating because they are essential for delivery of data of known accuracy. Topic 2.3.3 explains the importance of post-event accuracy checks. And finally, topic 2.3.4 discusses the frequency of calibration activities. Instruments and sensors used for scientific measurements are often based on sensing differences between 2 compartments through conductance of electric currents. In the pH and dissolved oxygen electrodes, one compartment is full of a concentrated electrolyte solution, which interacts with the external medium, such as your creek water across a partition. An example of this would be the semi-permeable membrane of the DO probe. The electrochemical equilibrium, or balance across that partition, has to be reestablished every time the current is turned on, and it changes over time. Your pH probe has probably been calibrated by the manufacturer, as shown on your screen in the image on the left. The instrument reading, as shown on the vertical y-axis, was the same as the theoretical value of the standard buffer, as shown on the horizontal x-axis, and this linear plot had a characteristic slope. Over time, small changes in the internal environment of the probe cause the value of readings to drift away from the calibrated state. This drift can be the same across the entire pH range, as shown on your screen in the center image. If you adjust the reading of your instrument now, for example by using pH 7 standard buffer, you will bring it back to the calibrated state for the entire pH range. However, the shifts in electrochemical equilibrium may be different in different parts of the pH range, causing the slope to drift away from the calibrated state as well. You can see an example in the right panel on your screen. If you adjust the reading of your instrument by using only the pH 7 standard buffer, you will bring it back to the calibrated state at pH 7, but it will still be off for the rest of the pH range. To bring your instrument back to the original slope, you must adjust the reading at more than one point. This is why you are always asked to perform at least a 2-point calibration, and better yet, a 3-point calibration on your pH electrode. If you do a 2-point calibration, make sure you use standards at values that bracket the anticipated pH in your stations. Please remember that you always have to check the instrument's reading in the standards after you come back from the field, or within 24 hours. This number will be used to calculate the drift associated with the measurement results you have obtained during the trip. The accuracy of your measurements is directly related to the standards you use and to the drift of your instrument. To be able to share this information about standards and drift with others, you have to capture your calibration records on a data sheet or a spreadsheet. Any good data sheet you use to record the results of accuracy checks and track the calibration adjustments made to your instrument will have placeholders for the following information: the unique instrument ID or serial number, the date and time of your operations, the standard material that reflects what we perceive as the true value. This can be the standard salt solution for calibration of your conductivity probe, or the standard buffers, or the DO saturated humid air you use for calibration of your DO probe. The reading of your temperature probe cannot be adjusted, like several other non-adjustable instruments you may encounter, and for these you can only do an accuracy check against a certified thermometer. True value of standard material. The reading of your instrument in the standard material before any adjustments. The action taken, adjusted or not, and the outcomes of calibration adjustments. The operators. When using sophisticated instruments like the YSI sones that many swampers use, you are encouraged to capture the operating specifications of individual probes. For example, the voltage applied to the pH probe, and to verify that the probe is performing within the acceptable limits. Please refer to the manufacturer's instructions and to the instrument calibration PowerPoint presentation in the SWAMP toolbox for further detail. For a selection of the SWAMP datasheets and generic datasheets for use as an alternative, please go to the SWAMP toolbox. Instrument calibration, where possible, is a means of controlling your accuracy. After you come back from the field, you will need to check your accuracy. Simply put, in the morning you adjust the reading of your pH meter to the true value. Then you do your field work. And in the evening, you put the pH meter in the standard solution again and record what it reads before any adjustment. Naturally, you can use the same form to record the results of accuracy checks. Now, all the measurement results that you collected that day with your pH meter fall within a bracket of time for which you have information. If the instrument drifted from the calibrated state between the morning pre-event calibration and the evening post-event accuracy check, you know by how much it drifted. While you do your post-event accuracy checks, and you already have your probe in a fresh standard, you can also adjust the reading. If your trips are back-to-back within 24 hours, this action can become the pre-event calibration for your next trip. To find out more about the importance of accuracy checks and the way you can affect, check, record, and report the quality of your measurements, click the Go to Quality Assurance button. Instrument calibration is a means of controlling your accuracy. You can improve your accuracy by calibrating your instruments often, because you will not let the instrument drift much. We all assume that when an instrument drifts from its calibrated state, it moves in one direction only. However, we cannot know it for sure. SWAMP recommends that you calibrate your adjustable instruments every time, within 24 hours before you go on a trip, and check it when you come back in the evening, or within the next 24 hours. When you deploy data loggers, you practically do the same. Calibrate up to 1 day before taking it out, and do the accuracy checks within 24 hours of retrieval. When you are using a dissolved oxygen electrode for discrete field measurements, you may need to calibrate it several times a day. You certainly need to calibrate it if your stations are in different elevations, every time you gain or lose more than 500 feet of elevation. Some types of pocket meters, for example conductivity meters, drift out very slowly, and experience tells us that we can check them every other trip or so. The most important thing is to capture the calibration adjustment records every time. Pocket pH meters need to be calibrated every morning before monitoring, and checked as soon as possible after the trip, because experience tells us that they drift a lot. How often do you need to perform accuracy checks for your non-adjustable instruments, such as temperature probes, bulb thermometers, calorimetric nutrient kits, or pH strips? Periodically. Field observations, such as flow conditions or water murkiness, provide a treasure trove of information on a waterway and take a very short time to perform. Some field observations are essential for interpretation of measurement and analyses data and should be done on every visit. The table on your screen shows some examples of words SWAMP operators use to describe what they see or estimate. You can always add information about other environment aspects, such as the color of the water as viewed in a clear container, the wind conditions, whether it is calm, breezy, or windy, or whether the creek is clogged with leaf litter. Please consult the SWAMP toolbox for the latest database-ready options. This topic has two screens. The first screen, Topic 2.5.1, lists the types of habitats that need to be considered when selecting the exact place to put the probes when conducting water quality measurements and what the inherent variability can be. Topic 2.5.2 suggests what to do if you cannot access that place with your probe. One of the main challenges field operators face is to find the centroid of the flow, which is the line that separates the flow discharge into two equal parts. It is often the most representative spot in the channel. There is more information on centroid flow and stream habitat types in Module 4, Section 4.1.2 of this course. To read more about the subject of representativeness, please visit Common Element C of this course. Natural stream channels have many types of habitats, and under low flow situations, the water quality conditions may vary in different habitat units. The graph on your screen shows results from a creek walk in Wildcat Creek during summer, when flow discharge was about 2 cubic feet per second. As the team moved upstream along the centroid of the flow through a sequence of pools, riffles, and step pool habitat units, they recorded values that differed from each other by more than 0.3 pH units, and by up to 3 milligrams per liter of dissolved oxygen. These and many other similar tests show that it really matters where in the creek you put the probe. On the same walk, the dissolved oxygen measured in an isolated side pool was below 3 milligrams per liter. In nutrient-enriched streams, backwater pools often harbor large masses of algae that can drive the dissolved oxygen and pH values to extreme highs during the day and to extreme lows during the night. You also need to be aware of subsurface flows emerging from the gravel, for example, when the tallwig hits bedrock, and be aware of groundwater seeping into the channel at various locations. Those inputs can produce unexpected temperatures and other dramatic changes in water quality. The water near the edges of waterways, also known as edgewater areas, can be quite different from the main flow if there's not much mixing. Edgewater areas are a severe problem where scum and litter can accumulate and often have impaired water quality conditions as compared to the centroid. It may be worthwhile to invest some time to characterize the immediate vicinity of your monitoring station to select what you believe is the spot that provides a good representation of the prevailing conditions in that reach. As mentioned above, there is more information on centroid flow and stream habitat types in Module 4, Topic 4.1.2, and more examples of representativeness in Common Element C of this course. In California, during low flow conditions, you can usually wade into the habitat units of interest and away from all edgewater areas to perform the measurements with the probes directly, otherwise known as in situ. Go to the next screen to see access options and examples of things you can do when wading is not possible. Now that you have a sense of where in the water body to make the measurement, you can go ahead and wade to that location to conduct the measurements in situ. In situ is Latin, meaning something like in the site itself. If you cannot wade, you can stand on a bridge or a dock and throw a clean bucket tied to a rope to bring some water up to where you are, and immediately put the probes in the water to take the measurements. You can also extend your reach from the bank, any bank, by 12 or 18 feet if you have a telescopic pole attached to a beaker. This is often the only way you can avoid measuring or sampling edge water when you cannot wade. Click on the top button to see a video of the use of sown probes in situ. Then click on the lower button for a demonstration of the pole and beaker device, which can be used to bring water from the centroid in a beaker to a field operator on the bank for probe measurements.
Okay, Sean, you ready? pH 8.06.
8.06 pH.
Dissolved oxygen 9.76.
9.76 milligrams per liter dissolved oxygen.
Conductivity 367 microsiemens.
367 microsiemens.
And temperature is 17.68.
17.68 temperature.
And I just want to demonstrate another device device which will allow you to collect a sample in the middle of the stream even if you don't want to wade in. You get a pole in the paint department of the hardware store. You get a brush holder and a little bit in a container from the supermarket, and you can create your own sampler. All these pieces fit together. Now, if you get a telescopic pole, you could actually extend your reach by to about 12 feet, all the way into the center. And the way you use this is very simple. This way, now you can go, you can actually reach wherever you want. You can collect, wash your sampling device 3 times. Collecting the water under the surface, washing it 3 times downstream, and then bringing back the sample.
What you see on the screen is an example of a measurement block taken from a generic field data sheet with routine water quality parameters, using units and capturing information required by SWAMP. It shows what needs to be captured with any instrument beyond the station ID, date, field crew, and other information about the visit. You might see a different layout of the information boxes on a different data sheet, but make sure the information content is the same. This example shows a convenient format for use with a personal digital assistant, or PDA, if you want to write the data directly into a spreadsheet in the field. The procedures of measuring water quality parameters are varied and instrument-specific. However, there are several do's and don'ts that are common to any field measurement. If you dip the probe in and out a couple of times, and shake it in the water occasionally, you will get rid of air bubbles and replace the liquid around the sensor, so it really sees your water sample before you take the measurement. Watch the reading for a while, observe the changes, and record the result after it has stopped changing. Dissolved oxygen and pH electrodes may take several minutes to stabilize, and in many cases, your accuracy or precision will be a direct function of your patience. Pocket conductivity meters with automatic temperature compensation may have temperature probes that are hidden behind a thick layer of plastic and need a good few minutes to sense the real temperature, so the instrument can accurately compute the specific conductivity. If you are using a dissolved oxygen electrode of the Clark type, you must keep stirring the probe vigorously and constantly, because the electrode consumes oxygen while measuring it. Never drop your probe onto the stream bed, and always keep it out of the sediment. If you accidentally disturb the sediment, move to another spot. If your probe touched the sediment, check it to make sure it is not damaged or covered with dirt. When waiting to do the measurements, always move upstream and extend the probe as far as possible ahead of you. When using a sampling device to bring a sample of water closer to you, you may rest the probe on the bottom for temperature equilibration, but never let the probe touch the walls or the bottom while taking the reading. Always have clean water with you, preferably deionized or distilled water in a squirt bottle. Rinse your probes immediately after use whenever you can, and never let them dry dirty. Remember that removal of dry crud is much harder than simply rinsing right after use. If you intend to deploy data loggers for continuous, unattended monitoring of basic water quality parameters, you have a lot of homework to do. Most zones come with a big binder of instructions, and they may be specific to each model. The procedures for calibration, programming, deployment, and protection are complex and specific, and this module cannot provide that information at the desired level of detail. There are many swampers out there who would be happy to share information about the items listed on your screen. If you have a YSI zoned, you can view the PowerPoint presentation on your CD, as prepared by Peter Otis for his training class. Contact RB3 for information about Hydrolab zones and deployment durations. And always look out for new technologies, such as a miraculous dissolved oxygen probe that never requires maintenance.
STV 35 reads 564 micrograms. was at Micro Siemens 500N.